Hello, my name is Yanshuo Wang. Here's my great honor representing all the co-authors to introduce our paper, Continual Test-time Domain Adaptation via Dynamic Sample Selection. Let's begin with a short introduction. Continual test-time domain adaptation aims to gradually adapt a pre-trained model to a sequence of target domains without accessing the source data. As an example, imagine we have been given a trained source model designed for shock classification, and our task is to apply this clean model to various types of corrupted shock images during inference time without the need to retrain models. Existing methods are mostly based on self-training and entropy regularization to adapt the model, and they can suffer from the continually changing domains in adaptation. To be specific, model adaptation is performed during test time based on unlabeled test samples, and they normally rely on sample pseudo-labels for the adaptation. However, not all pseudo-labels are reliable, as the wrong pseudo-labels arise from the continual domains. The network tends to absorb inaccurate feedback, leading to inaccurate adjustments of its parameter over time. This accumulation of errors from the previous domains would have an adverse impact on the model performance in the subsequent domains. To help the model adapt to continual domains with less error accumulation, we propose a new adaptation strategy named Dynamic Sample Selection to monitor the pseudo-label generated and identify trustworthy information. Here we illustrate the difference between previous approach and our approach. On the left-hand side, it is the previous approach, and on the right-hand side is our approach. The previous approach is treating all samples equally, and the incorrect pseudo-labels will lead to error accumulation. In contrast, our DSS excludes low-quality pseudo-labels generated using a dynamic thresholding process, and then positive learning and negative learning are separately applied to reduce the risk of propagating misleading information. Here we show the overall framework of our DSS module. DSS mainly consists of two parts based on the teacher-student setup. The first part is the dynamic threshold, and the other one is the positive learning and negative learning. Given the input xt from the test-time domain dt, the teacher model first computes the pseudo-label based on an argumentation module, while the student model produces the unargumented output. The model is then trained using losses between teacher and student predictions that enforce consistency. The final prediction is given by the more robust teacher prediction. As mentioned earlier, we do not treat all samples equally for adaptation in training. In contrast, we assume not all samples have enough quality for training during test time. To achieve this objective, we utilize a dynamic threshold module to modulate the adaptation progress adaptively in each iteration and every time we encounter new domains. In short, we build a DSS framework on top of the student-teacher model to select samples for different learning strategies. First, to design the threshold mechanism in test time, we adopt a threshold based on confidence measurement to dynamically exclude unreliable sample. The estimated global threshold pi represents model confidence on unlabeled target data over time, and it is calculated as the exponential moving average of the confidence at each iteration. Lambda represents the moving average factor. To further reflect the discrepancy between the adaptation status among different classes, we further give the threshold in a classwise manner to ensure that the class with the average low confidence is not ignored. We compute the weighting factor tau for each class C as the average confidence for each class divided by the largest confidence value of all classes. The final class-wise threshold is then calculated by multiplying the weighting factor and the global threshold. After splitting samples, different training strategy will be used. First, we restrict positive learning to the high-quality group XT high, as these samples are expected to have a higher probability of being accurately classified by the network. Note we mildly give these pseudo-labels by applying the sharpening instead of one-hot pseudo-label. It somewhat avoids overfitting by preserving the prediction structure from the teacher model. The loss function for positive learning is then formulated as the cross-entropy loss between the teacher and student predictions. On the other hand, negative learning is applied to mitigate the risk of providing inaccurate information to the model by generating the complementary label. The complementary label is created based on low-cost confidence, and it represents the input does not belong to classes. This provides more reliable information regarding the classes that are most likely not to be the true label. In other words, a prediction that is potentially considered wrong is replaced by a negative complementary label. Following this, we present the negative learning loss using negative cross-entropy loss as following. Y reverse hat is the complementary label based on the prediction from the teacher model. And the final loss is calculated as the sum of the negative learning loss and the positive learning loss. Finally, we show the DSS performance on 3 different 2D datasets, CVAR10C, CVAR100C, and ImageNetC. From the table below, our DSS has lowest error across the board, which indicates that DSS enhances the model adaptability across different domains and different datasets. Where our method is designed to address the continual test-time domain adaptation for 2D image recognition, we also adapt and evaluate our method for the case of 3D point cloud recognition. Here we could also see that DSS still helps to adapt model for point cloud recognition. So in conclusion, we introduce our method termed dynamic sample selection based on joint positive learning and negative learning with a dynamic threshold. It aims to help the model better adapt for continual test-time domain adaptation with less error accumulation. Thanks everyone.